Thank you very much. So the purpose of this presentation is, I'm imagining most of you in this room don't know what Open vSwitch is. So I'm going to quickly describe what it is, very briefly how it works, and then go through some examples of some of the features it has that makes it interesting. So, I already covered that one. So what is it? It's a multi-layer virtual switch. What does that mean? It means that like a physical switch, it operates at layer 2, but it can also operate at layer 3 and layer 4. So you can direct packets based not only on the MAC address, but also, for instance, the IP address. It's a software implementation. It's purely software. It runs on a commodity hardware running Linux. It has a controller running in user space. So this is the decision-making engine. It has the data path in the kernel, so this is what actually passes the packets around, and it's quite fast. Perhaps not as fast as a hardware switch might be, but as fast as Linux networking is. It's an implementation of a protocol called OpenFlow, but it actually implements a lot of features which aren't in OpenFlow. Where can I get it? OpenVSwitch.org is the place to go. All of the code is available in Git. The data path is going to be included in Linux 3.3, not 3.2, as it says up there. And there are the announcement, discussion, user mailing list. It's a very open community. There's a company behind it. I'm not associated with those people in any way. I am just a member of the community. So the licensing is important, I think. The user space tools are Apache license. The kernel portion is GPL because it needs to be compatible with the kernel. And the bits that go in between, the shared header files, are both. So we need to, there's a few concepts you need to understand in order to be able to discuss what Open vSwitch does and how it works. So a switch contains ports. So if we think of a physical switch, I'm sure you've all seen one, that would be the holes where you plug in the Ethernet cables there. Actually, that's not true. The holes would be the interfaces. A port may have one or two interfaces. So really, the difference between a port and an interface is that you can use a technology like bonding to create a port that uses multiple interfaces. Usually, each port has one interface, but you may have more than one. And packets are forwarded on the basis of flows. So a flow, so if we think of a very simple switch, a flow will be defined by the destination, source and destination MAC address. Flows may be defined by any of these things. I'm not going to read out that list, but you can see it's quite long, and it includes source and destination MAC addresses, but it also includes a variety of other things from including the source and destination IP address, which is not information that will be normally done in a layer 2 switch. So this is really this ability is one of the key things that differentiates Open vSwitch from the existing bridging implementation, which has been in the Linux kernel for many, many years, is the flexibility that all of these keys allow you. So when a packet comes in, when a frame comes in, how does Open vSwitch work? How does it deal with it? Well, firstly, it doesn't say this up there, but it hooks into the Linux kernel at the same place that the Linux bridging code hooks in. And that place has been extended slightly to allow it to be shared. But essentially, it's bypassing all of the Linux routing code. So the very first packet that comes in for a flow, not obviously, but the data path doesn't know what to do with it. The data path is not a particularly intelligent thing. It will see this flow packet come in. It does a hash table lookup, and it discovers that it doesn't know anything about it. It then sends that packet, which it doesn't know anything about, down to the user space controller and forgets about it. It doesn't wait for a response. It just sends it, and it gets on with whatever the next thing it has to do. The controller then reads this packet and makes a decision based on whatever rules have been configured. So if we're just doing a simple MAC-based learning switch, it will look at the destination MAC address and make a decision based on that. Or it may decide to flood it. Whatever it decides to do, it then tells the data path. Whatever it decides that should happen to packets belonging to that flow. So by teaching the data path, it teaches the data path how to match that flow and what to do with packets that match that flow. It then, so that's stages 1 and 2. Then lastly, it sends the packet back up to the kernel because the kernel has forgotten about that packet. It just sent it down to user space and that's it. If the controller wanted to drop the packet, it would just do nothing. Okay, so now these packets come in. There's been a bit of a delay here, so this is a potential performance problem. And then it's sent the packet on. Okay, that's nice. So if we think of a TCP connection, essentially the other end will be waiting. There will be no, unless this takes an extremely long time and there's a retry, we'll just wait. The connection will stall for a few microseconds and off it goes. The next packet that comes through, it already knows what to do because it's already in the data path. So this fourth packet, or this fourth stage, which is the second packet, just goes straight through. It just does, the kernel does a hash table lookup, realizes that it knows what to do, and does whatever the hash table lookup tells it to do. So this forwarding is very quickly, it is very fast. This is your fast path. This stage 1, 2, 3 is slow, and that's just the way it works. Okay. So how do we manage this thing? It's important to be able to configure things, otherwise we have no control over what they're doing. So it's configured by a JSON database. The fact that it's JSON isn't particularly remarkable, but the rest of it is kind of interesting. It's persistent across restarts. So if we think of something like the Linux routing table or the Linux bridging code itself, if I reboot my machine, I do not expect my routing table to magically reappear unless there's some init scripts to reconfigure it. In this case, we have a persistent database which is in user space. And so whatever I configure now, if I restart the daemon or I restart the whole machine, it will be there again. So this is kind of cool. In order to configure the system, what we do is we connect to the database, and then the database connects to another part of the system. My call to the database won't return until that action has that configuration action has either failed or has successfully completed. So we can rely on the fact that if I ask the database, please add a new bridge, that by the time it says, yes, I've done it, it's actually done and it's ready to work. So this is interesting because it allows us to, for instance, configure the database remotely and rely on the fact that we don't have to worry about how long it's taking and guess how long that communication. We know that when the message comes back, it's done. And yeah, so this is the last point. Usually you configure the database using a Unix socket for efficiency reasons, but it can be remote. It can use TCP, and that TCP connection can optionally use SSL. So I think this is kind of cool. Okay, so what does it look like? I'm not sure how many of you have used bridging, but let's say we want to add a very simple bridge. Like we create a bridge and we add a port. This is the simplest thing you can do. So firstly, we need to make sure the user space portion is running. Ordinarily, this would be done on init, but this is fundamentally different to the way the bridging code works, because the bridging code only exists in the kernel. There is no user space portion. And we create a bridge. I like this may exists optional argument because it makes the operation idempotent, which means I can create the bridge. The bridge creation action will succeed even if the bridge already existed. So sometimes I lose track of what exists, what doesn't. It's easier to use this and to test to see if it exists and then create it if it does or it doesn't. It just may exist. And again, may exist is here and we add a port. So this bridge 0, now has one port, which is Ethernet 0. There we are. Oops, what happened here? Going the wrong way. Okay, so after all of that, we decide we don't want it afterwards. We want to modify it. We don't want Ethernet 0 to belong to the bridge anymore. No problem, remove it. We decide we don't want the bridge at all. We can just remove it, and which implicitly runs this action, because once the bridge is gone, nothing is a member of it anymore. So that's kind of interesting, and this maps very closely, apart from this part, the user space part, maps very closely to the bridging code. Now, in practice, you wouldn't really use this because if you're just doing what the bridging code can do anyway, why would you bother? But you can. Okay, so now I'm going to look at some more sophisticated configuration options, which hopefully will give you an idea of some of the more interesting things you can do. So I'm going to talk about 4 things. I noticed while I was preparing this talk that actually this maps very closely to the man page. I apologize for that, but it was not intentional. Okay, so what's VLANs? Fundamentally, VLANs are a method of partitioning a physical layer 2 network into multiple logical layer 2 networks. It's a pretty old concept. I imagine many of you have some experience in it. There are 2 types. If I have a switch and it's configured to use VLANs, each of the ports can be one of 2 types of ports. It can be an access port or a trunk port. Now, an access port does not use tagging. Whatever you've plugged into that, maybe some sort of desktop equipment, anything. It's completely agnostic over the wire. Only packets for the configured VLAN will appear on that wire, and the switch makes sure that that occurs. Okay. A trunk port makes use of tags to allow you to have multiple VLANs using the same port. So for instance, if I had 2 VLANs on this switch and 2 VLANs on this switch, and I want them to communicate to each other, I can just use a single link between the 2 switches and make use of trunking. So, how does this relate to Open vSwitches? What we can do is by providing a tag, the tag is the VLAN ID, by providing a VLAN ID when we add a port to a bridge, we turn this into an access port. So if the bridge receives, so imagine a bridge where there's 2 ports. There's a physical port, and then there's this access port we've just created. If anything comes across the physical port, which has VLAN tag 7, it will go to that port. If it has any other tag or no tag at all, it will not go to this port. Okay, so we can basically partition our network, and that's kind of nice and exciting. So this is an example of something that is, I don't actually believe it's possible to do with bridging. I could be wrong, but because of some quirks in the way that the Linux network stack works, when you're using bridging, you essentially need to associate your IP address with the bridge itself, not with ports attached to it. And this is because the Ethernet link layer addressing is stripped off at inappropriate moments if you're not using the right port. So this is why I believe you can't simply create a bridge and attach a VLAN interface for it. You need the bridge itself to understand the VLANs. And internally what this does is it sets up the data path with some actions to strip off the tag or attach the tag and match it as necessary. Okay, so span is another technology that I find quite interesting. So the idea of span is that you can mirror traffic from one or more ports to another port. Now, why on earth would you want to do that? Well, let's imagine you have a scenario where you have a router, perhaps you have a small office, and you want to somehow measure the traffic that's going through this router for some reason. The router itself it's not a nice Linux box. It doesn't have facility to do that. So you can approximate what's going on there by just observing all the traffic that goes into the router on its Ethernet port. Okay, well, how do you do that? Back in the good old days, back in the not so good old days when we just used hubs, you would just simply plug a machine nearby and sniff the traffic. Bingo. Can't really do that anymore because everyone uses switches. So what do? Do you somehow try and get a hub involved in this equation somewhere? Do you plug a Linux box between your switch and your router? All of those things would work fine. Or you can use span to basically mirror all the traffic from the router port to another port and then just sniff that. Okay, so it's kind of cool. There's also a remote version where you can potentially sniff on other switches, but that's not, I don't believe you can do that with Open vSwitch easily. So how do we do port mirroring? How do we do span with Open vSwitch? Okay, so firstly we need we don't have a physical switch. We can't just plug things in. physical things, but we can plug as many non-physical things as we want. So we create this dummy interface. Now, dummy interface in Linux is just a sink, basically. You can put stuff in there, and it's like DevNull for networking. But you can use TCP dump and tools like this to watch what is going down the sink. So this is a pretty good match for what we want to do. It's very efficient. And okay, so we create, this just adds dummying to the kernel, and then we activate the link because you can't TCP dump a link that's down. And then we add that to our bridge, which we created a little bit earlier. Okay, so it's all sitting there. It's not doing anything, it's just sitting there. Okay, so now, how do we tell the system that, please, we want to use mirroring? So, okay, I gotta explain this syntax a little bit because it's a little bit special. Firstly, the double dashes allow you to string multiple control commands together in a single invocation of the tool. So each line here, other than the first line, corresponds to a separate command. That's thing number one to know. Thing number two to know is this bizarre notation here with the @ sign and the P, and it's over here too. What is this? And there's another one, M. These are variables. So what we're saying is, so this get port command, what it does is to fetch the ID, the internal identifier of that port, and stuff it in this variable called P, which we can then use down here. Okay, so the output of this is used as the input to this, and the output of this is used as the input of this. Okay, so now hopefully we can read the syntax if we. So what are we actually doing? We find the UID of the target interface, and we say that. Then we create a mirror. So a mirror is just it's actually just an entry in the database, but it's a conceptual thing of, we're going to mirror some traffic, we need a way to store that configuration, and that will be stored in a row of the mirror database called mirror0. Okay, so we've created the mirror. Now we're going to configure the mirror to do something. So we add we have the mirror, but it's just sitting there by itself. It's not attached to anything. So now we need to say, this mirror will be used on bridge 0. So that's what the third line does. So this bridge has a list of mirrors, which was up until now empty. And now we've added one mirror to it, which is the one created on the previous line. Still not really doing anything, but we're building up the configuration. And now lastly, we say this mirror, any traffic that it's configured to mirror will be output to port P, which is the dummy interface, which we looked up a little bit earlier. So we've created a mirror, we've attached it to the bridge, and we've said its output will be on our dummy interface. Okay, so far we know we have the mirror set up, and we can put packets out of it, but we don't actually have any packets. We haven't configured it to collect any data. So that's the next thing. We look up our tap interface. So this is just going off to a virtual host. It could be any interface we're interested at all, but it's just an arbitrary example. And we say, any packets that are going into that interface, so I address to that interface we're interested in, and also on the next line, any packets that are coming out of it. So all packets going in and out of that port. Okay. So that's it. It now works. And I will demonstrate that hopefully in just a moment. The other way you can do this, last step, is you can just say, I want to mirror everything that's going through this switch, apart from obviously the destination port, because otherwise it would get into a loop. I want to see all of it. So that's kind of cool too. I guess if you only had one port, that would be a shortcut, but I don't know. I think this one is more interesting. So I'll see if I can get that working for you. Okay, so I made a few little scripts to make this a little bit easier. Okay, so what are we doing? Okay, hopefully we can see that. So this just sets up the basic networking. These lines here just make sure it's in a known state. And then we create the bridge, and then we get an IP address. We'll see if this works. Okay, so we're now configured. So we can see our Ethernet interface. Maybe you can't see that. You can see the Ethernet interface is up, but it doesn't really have an address, apart from the IPv6 link local one. And we can see that an address that we might ordinarily expect to be on the Ethernet address, Ethernet interface, is over here on the bridge interface. And if I ping something like myself, it's working. Okay, that's wonderful, great. Next stage is to try and set up some mirroring. So how does this work? So we're going to create our dummy interface, and we're going to add it to the bridge. This is the configuration I described just before. Okay, that's also working. There's no error. And so we can see that if we want. So this just shows us the mirror table in the database, and we can see it's got one entry which is called mirror, and most of its data is empty. Oh, sure. I will make the font larger as requested. Okay, that's as big as it goes. So that's what the database configuration we've created so far. So lastly, we'll try and activate this. Well, yes. So the activation is to tell the mirror that everything from ETH0 should be mirrored to the dummy interface. Okie dokie. So with a bit of luck, I must say I'm not really very keen on giving demos because I feel that they always go wrong, but let's see. So up here, I'm going to try So up here, I'm running TCP dump on the dummy interface. And you just have to take my word for the fact that that is all the traffic that's going through ETH0, which is being mirrored over to dummy 0. It's quite a lot. So I could run some filters on that. In this case, it's kind of pointless because I could just sniff the Ethernet, the ETH0 interface directly. But I hope that that kind of illustrates things a little bit. Where did my presentation go? Okay, so that's mirroring. Okay, so I have two more topics, but I'm running out of time, so I'm going to skip one of them. I'm just going to do tunneling. This will be the last one. Tunneling allows you to take two L2 networks, which are separated by some kind of routing, and join them together. Well, why might you want to do this? The room might be full. You might have your server room might fill up. You might want to put some machines somewhere else. For some reason, there's routing going on between those two rooms, but you want them to use the same L2 network, at least in a limited extent. You could also use it from a remote access. If, for some reason, you felt like you wanted to have an L2-based VPN instead of an L3-based one, you should be able to do it. It supports GRE, which is a very popular tunneling protocol that you can use to tunnel almost anything. And it also supports VXLAN, which is a relatively new addition, which has been developed because some switches aren't smart enough to do GRE, physical switches aren't smart enough to do GRE in an intelligent manner, so you end up with a lot of flooded traffic. I think what I would describe as a hack. Anyway, how do I set up tunneling? We create an interface. We call it GRE, 0. Its type is GRE. This is the most important thing in the whole thing. If I wanted to use VXLAN, I'd just call it VXLAN. Its remote IP address, so the other end of the tunnel, is 10.0.0.8. The local address is 10.0.0.9. And the key, GRE tunnels can have keys, so you can have multiple of them, is number 1. Then we create a port that uses this interface, and then we add the port to the bridge. Bingo. This information here, the local IP and the key, is not strictly necessary. If you're only planning to use one tunnel between the same endpoints, you don't need the key, and you don't really need the local address at all. So I didn't realize that initially, but here you are. The other end, obviously you need to configure the other end. There's not much point otherwise. These addresses have been exchanged. Everything else is the same. And again, you don't need these addresses. You just need this. So you just need to know the other endpoint, really. There we are. I'm not going to demonstrate that but you can send packets between two endpoints. And you can also throw IPsec into the mix here. So there's a bit of a security theme in the keynote this morning. So you can communicate between your two endpoints in a more secure fashion. I didn't include how to do that because I haven't actually done it, but I believe it works. Okay, so I'm not going to go through QoS. Feel free to come and ask me about it later. But suffice to say that you can have per port QoS policies if that's what you want to do. Thank you very much.
Thanks for the talk. That was very informative on the details of it.
Right.
Can you give some examples of the real-world usage it's used for?
Sorry, I meant to go through that at the beginning. Why would you use this? So the initial target is virtualized networking. So let's imagine you have a host and it's got various guests on top of it. And usually when you have guests, you want them to have some kind of network connectivity. Perhaps you want to sell them to people. The bridging code can already do all of that, but the idea is that essentially in those kind of in multi-tenant environments, there are things that you might want to do, like VLANs, which the bridging code is not well suited to. And rather than continuously extending the bridging code and which is entirely contained in the kernel, to move the logic down to user space to give us more flexibility. There are other uses for it. Because it's a general framework, people have discovered all sorts of weird and wonderful ways to use it. But the original aim was virtualized network environments.
What weird and wonderful?
So you can basically use this to create a virtual network that is independent of all the underlying hardware. You can use it to basically eliminate routing from what's going on in your Linux box, if that's what you want to do. To be honest, I understand the plumbing much more than I understand how to use it.
Can you, say, rewrite a VLAN tag? The use case is if you've got an upstream provider that's providing a wide area network over a VLAN.
Sure. So the answer is, can you rewrite VLAN tags? And I believe that to be true. And if it's not true, it will be very easy to add. Yes?
Can you use EB tables with it?
Can you use EB tables with it? I believe the answer is no. But you could do some of the things EB tables does, like dropping packets, using the provided mechanisms.
Just to note that it's our intention to embed Open vSwitch into Oracle VM. So we are actually going to switch from base Linux bonding and bridging across to Open vSwitch in some future version of Oracle VM as well.
Oh, that's great.
The nifty thing about Open vSwitch over the base bridging code is that we can create virtual switches that span hypervisors. So on a cluster of Oracle VM servers, you get what is usually really expensive in the Cisco world is the switches that actually talk to each other to create, sort of multi-trunks and stuff like that. So that's very nifty for that in the virtualization space.
Thank you. That's very exciting. I didn't know that.
We're taking it to production in UEK too as well. So.
Do you know if anyone's doing any open hardware to make 24-port, 48-port switches that run this stuff?
Okay, so the OpenFlow protocol is, which I only mentioned briefly, is designed so you can have the controller part in software and the hardware as a black box. I think that's the closest we've got to. I'm not aware of any open hardware projects.
Toward the start, you were talking about how the first packet that comes through, the controller then tells the kernel what to do with it. Does the kernel expire those rules, or is that up to the controller? How does that work in terms of expiring?
Expiry, oh yes. So after the controller teaches the data path what to do, and yes, it's just a simple timeout on it. I think the default's maybe 10 seconds or a minute, something like this. So it has, but only if it hasn't seen any packets.
What's that cache keyed by? Is it keyed by the hardware addresses? Because you talked about a whole bunch of different matching.
How is the flow table lookup done? Actually, I don't know what the hash key is. I think it must construct the hash key from all the possible. Any entry in the hash table. So in the controller, you can have wildcard entries. So if you don't care about the IP address, that's just anything. In the kernel, all the fields are fully populated.
Right.
So in the controller, you could have one rule that covers all traffic that you will ever see. In the data path, every single unique endpoint, or every single unique flow will have its own entry. So it's an exact match. So I think the hash key would involve looking up all the fields.
Okay. Which makes it potentially a little bit more expensive if you're just doing basic bridging. If it has to trawl through the headers.
Yes, potentially the lookup is more expensive than bridging because it would suck in more of the packet.
If you're just doing basic bridging, though, you just use the...
Yeah, if you're just using basic bridging, you might just use the... There's no plans to get rid of the bridging code. So.
No, I was just using it as an exaggerated example.
Right. I think in practice, you would have to be doing rather high packet rates to notice that. But it's a good point. Yeah. Any more questions? Yes.
How scalable is this in terms of both performance and kind of management to visualize all these single port kind of configurations that you've created?
Right. So how scalable is this? In terms of management, I believe the way that it's set up allows you to create a scalable interface, but I also believe no one has done so. So I think the current answer is not yet. Were you also asking about packet rates and things like that? And I've also done some work on packet rates. So the key bottleneck is the rate at which you can create new flows, because that has to go across that user space boundary. I have done significant work in improving the performance of that. So essentially, you used to have a bottleneck around a few tens of thousands of flows, and you just couldn't do anything more. It's now around a few, not a few tens of millions, but around at least a few million. So we've improved that a bit. The rate of packet of flow creation still needs some work. I have some packets outstanding. That's the thing that makes that, the scalability issue there is there are certain things that occur which, for instance, it dumps statistics on all the flows present in the kernel for account keeping, and obviously the more flows that are present, that becomes more expensive. In terms of packet rate, not flow creation rate, packet rate, I once came up with a number of 12 million packets a second, but I was never able to reproduce that. I don't know, I went to lunch and I came back and it wasn't working anymore, but I can reliably get 4 million packets a second without a great deal of tuning. The main limitation on this, again, is the controller, which is single-threaded, but if you're just pumping packets through the system, of course there's some hotspots in the code because it hasn't been optimized yet, because no one has really looked at this, but it should be possible to make it rather fast, I think.
What kind of hardware was that?
Okay, so the 4 million and the maybe 12 million I was using Intel 10 gigabit cards which were linked together using crossover cable. The tunneling has significant performance issues, which must be bugs if given the way the data works. So there's some work to be done, but it should be pretty fast eventually. Well, thank you very much for your time. I usually say, please come up to me afterwards and talk to me, but actually I have to leave the conference after this. But please send me an email if you have any questions. And thank you very much.
Everyone, thank you so much. On behalf of LCA Team 2012, we want to thank you for a good talk.
Thank you very much.